Hello, everyone. My name is Jiahao Zhang, and I am a PhD student at the Australian National University. Today, I'm excited to present our work, Manual PA, Learning 3D Parts Assembly from Instruction Diagram. This is a collaborative effort with my colleagues from Mitsubishi Electric Research Labs and the Australian Institute for Machine Learning. Our research tackles the interesting and challenging problem of enabling machines to assemble furniture by reading instruction manuals, much like a person would. If you're interested in our code and dataset, they are available as a GitHub link provided. I also look forward to discussing our work with you during poster session 2 on the afternoon of October 21st. So let's begin by defining the problem we are addressing. Imagine you have an IKEA assembly manual with a sequence of step-by-step diagrams, shown here as A along with a set of unordered 3D parts, shown in B. Our goal is to develop a model that can interpret the intent of each step in the manual and predict a precise sixth-of pose for every part. Ultimately, by applying these predicted rotations and translations, as illustrated in C, the model assembles all the parts into a complete piece of furniture that matches the one described in the manual. To understand the motivation for our work, let's first look at some related research. Methods like MIPNet have shown impressive results on tasks like Lego assembly, where they can construct models step by step by following a manual. However, these approaches typically rely on an autoregressive architecture. This means that the prediction for the current step is heavily dependent on the outcome of the previous step. This introduces a significant challenge, accumulating errors. As you can see in this illustration, any small mistake made in an early step can be propagated and amplified through all subsequent steps, leading to a complete failure of the final assembly. This brings us to the first core issue in our research. Given these ordered 2D instruction diagrams and this set of unordered 3D parts, how can we effectively learn the correspondence between them? This is fundamentally a cross-modal matching problem. Our solution to this problem is to employ contrastive learning. By learning a joint embedding space, our model can automatically determine which 3D part corresponds to which step in the instruction manual. Alright, so once we've established the correct part order through contrastive learning, the next challenge emerges. How can we effectively leverage this sequential information to guide the final pose estimation? We want to avoid the error accumulation problem seen in autoregressive models. Therefore, our answer is to use this learned sequence as a soft guidance. We achieve this by injecting it into our model via positional encoding, gently steering the model rather than rigidly constraining it. This slide provides an overview of our manual PA architecture. The pipeline consists of three main stages. First, in Part A, feature extraction. We use image and point cloud encoders to extract deep features from the 2D step diagrams and the 3D parts respectively. Next, in Part B, the order learning module, we compute a similarity matrix between the features from the two modalities. We then use the classic Hungarian matching algorithm to solve for an optimal assignment, which yields a permutation matrix representing the correct assembly order. Finally, in Part C, the post-estimation module, we encode the learned order into positional encodings and add them to the part features as a form of soft guidance. These features are then fed into a transformer decoder for deep fusion, and the prediction head outputs the precise rotation and translation for each part. Now, let's delve deeper into this concept of soft guidance. A key question is, why not use hard guidance? The answer is straightforward. If we force the model to follow a predicted order that might be incorrect, the model has no ability to self-correct. This would lead us right back to the error accumulation problem we aim to solve. This attention map vividly demonstrates the power of soft guidance. On the left is a chairback part. When we provide it with the correct positional encoding for step 5, its attention is sharply focused on the final fully assembled diagram, and the resulting prediction is accurate. But here's the crucial part. Even when we intentionally provide incorrect encodings for step 0 or step 2, the model is still able to shift its attention back towards the correct final step. This demonstrates the robustness and fault tolerance of our approach. So what about the other extreme? What if we use no guidance at all? In that case, the model would be forced to learn the correspondences implicitly on its own. This would significantly increase the difficulty and uncertainty of the learning process. This figure provides a direct comparison of the attention maps with and without order guidance. The top row shows the model without guidance, where you can see the attention is more diffuse, leading to inaccurate part placement. In contrast, the bottom row shows our method with soft guidance. Here, each part's attention is much more focused on its correct location in the diagram, resulting in a more precise assembly. Let's now turn to the experimental results that validate our method. This table presents the detailed performance on the PartNet and IKEA-Manual datasets. As you can see, across both datasets and against all prior methods, our manual PA achieves state-of-the-art performance on all key metrics. The improvement is particularly significant in the success rate, or SR, which is the most stringent metric for this task. This chart showcases the robustness of our method from another perspective. Typically, as the number of parts increases, the combinatorial search space explodes, making the assembly task much harder. The performance of other methods can be seen to degrade rapidly as the part count grows. In contrast, our method maintains a consistently high success rate across the board, demonstrating its strong scalability. Finally, these qualitative comparisons offer a visual confirmation of our method's superiority. It's clear that the assemblies generated by our manual PA are virtually identical to the ground truth. In contrast, other methods either produce results with noticeable geometric flaws or fail to correctly place occluded parts. Of course, our work also opens up several avenues for future research. The first challenge is moving from a category-level model, which we have now, to a universal model that can handle any arbitrary category of furniture. This is a very valuable direction for future work. Secondly, there is still a gap between the synthetic manuals we currently use and real-world manuals from IKEA. Real manuals feature changing viewpoints, multiple parts per step, and even complex sub-assemblies. Bridging this gap to enable our model to understand these complex real-world instructions is a key focus for our future work. To provide a more dynamic illustration of our assembly process, we have also prepared a short demonstration video which compares our method against image PA at each step of the assembly. That concludes my presentation. Thanks for your attention.